Okay. Let's let's start the class. Couple of logistical updates. The first homework is going to be out on Monday. You'll have 2 weeks to do your first homework. The second homework is going to go out. Okay, so Daniel's going to post today when the second homework is going to be out, when the midway project proposals are going to be due, and when the third homework is going to be out. Again, these are sort of dates that we're going to go by, but you know, there might be some flexibility in terms of changing roughly when, for example, the third homework may go out. But these are sort of the dates that we're going to try to stick to. One other update that I want to make in this class is regarding grace days. So I think we've basically, what we're going to do is we're going to give you 7 grace days for the homeworks and 3 grace days for the final project. Okay? Initially, I was thinking of spreading the grace days for the projects as well, but then there are issues that came out the last time when you have a group of 3 people, one person is late using all grace days, the other person hasn't used any of the grace days, and then there's a problem of what's fair, what's not fair. So since we know when the projects are due, I think they're going to be due on April 30th, and again, Daniel will post it. This is the due date, and you will have basically 3 grace days if you wanted to. Okay? So it's up to you. If you want to use the 3 grace days, you're more than welcome to use it. But please make sure that, and you have 7 grace days for the assignments. So please make sure for this course that you don't use all your grace days for your first assignment. You can do it if you want to, but I'm not going to be kind of, because it's going to be unfair like for other students, right? If you use your grace days, that's it. Even if you have a job interview the same day, or you have exams, or you have a conference you have to fly to, if you used your grace days, you're going to be penalized, okay? That's the goal of the grace days, is to make sure that you budget it yourself properly, since you know what your schedule is like. And I know many of you are going to be looking for jobs, or having conferences, or having midterms when the assignments are due, and all that kind of stuff. So make sure you plan properly, right? Because it happened to me multiple times when students come in and they say, I've used all my grace days and I have another midterm on Monday, and assignment 3 is so big and hard and it's due on Monday. Can I, turn it in on Wednesday? Okay? Any questions? Okay, so, and I think again, look at Piazza. Daniel's going to post exactly what the time schedule is going to be like for this class. Okay, so today we're going to look at temporal difference learning. We're going to look at the temporal difference learning. So last time we've looked at Monte Carlo methods, and today we're going to look at TD learning. So let's remind ourselves, what is it that we're trying to do? So we want to learn the value function, right? From episodes of experiences on the policy pi, right? So we have some policy, we want to learn what the value function is. So if we look at the Monte Carlo algorithms, we're basically going to be updating the value function toward the actual return, right? So what that means is that we start at a particular state st, we execute an action according to policy pi, we get the state, we again execute the action according to policy pi, and we look at the cumulative discounted reward up until the terminal state. These are episodic tasks, so they terminate. And then we look at the overall cumulative return, and that's the update rule. That's an incremental update rule for doing Monte Carlo sampling, right? You're just looking at empirical means. Now, the simplest temporal difference learning algorithm, something is called TD0, is the following. You're updating the value function towards the estimated return a step from now, right? So what is the estimated return? Well, if I take an action and I get to the next state, I might receive the reward at the next time step, and this would be my estimated cumulative return, right? Discounted by factor gamma. Because value, remember, the definition of the value is expected cumulative reward, right? So this term here is called the temporal difference targets, TD target, right? So this is what your target is. This is your estimated value of what the return is, and then you're just updating it, bringing it closer towards your value at current time step t. Okay? So it's worth looking at this particular formulation, right? Because something interesting happens. It's like your target here is your own estimated value of what that target should be, right? Which is a little bit weird if you think about it that way. It's like, think of a supervised learning. In supervised learning, I give you an image and I say it's a cat, and there's a true label, whether it's a cat or a dog, right? Here it's kind of, you're predicting something and then you're saying it might be a cat, and then you're asking yourself, according to your model, what do you think is this? And your own model thinks, yeah, I think it's a cat. And say, okay, good. All right. That's essentially what's kind of happening here a step from now, right? Now imagine the setting where your reward is 0. So you take an action, you don't get anything. So if your reward is 0, then you're basically just making sure that these two things are close to each other, right? And that hopefully will highlight also the settings where if you have a very delayed reward, so you're executing actions but you're not actually receiving any feedback, then even using TD learning, you're going to have, quite high variance in the estimates. Monte Carlo sampling is an unbiased estimate, right? Because you're basically saying, I'm going to be running it all the way through up until I get some signal, right? Temporal difference is basically saying, no, just one step look ahead, and I'm going to use my own estimates of the target to update my own estimate of the value function. Okay? And this term here, the difference between reward plus discounted value of the state at the next time step minus the value of the state where you're currently in is called the TD error, temporal difference. Or TD error. According to policy pi, right? You're always executing, you're taking action according to your current policy pi that you assume you have. Okay? Now, let's kind of step back a little bit and think about the differences between dynamic programming, Monte Carlo, and TD learning. Let's just look at the overall definition of the value of the state, right? By definition, it's the expected value of the cumulative discounted reward, G sub t, starting at state S at time t, and its expectation taken with respect to your policy, right? Where you're taking actions, and in principle, you also have to take an expectation with respect to the transition function, what the next state would be, given you're taking action and you move, what the next state would be. So we can write it down this way, right? Starting at state S. We can also write it down as return at time t plus 1 plus whatever the discounted factor is. And we can also kind of pushing expectations inside, we can write it in this way, right? It's the return plus gamma times the true value of the state, right? That's just the definition. Notice that this is the true value of the state st plus 1 under policy pi, right? That's just the recursive definition. There are no approximations, that's an equality, that's a definition. Okay? So Monte Carlo, what Monte Carlo does, you sample average return by basically approximating directly the top expectation, right? You're just simulating according to your policy pi, and your environment gives you the next state. So you're also sampling from the transition function what the next state would be. So you're just directly estimating the expectation at the top, right? And as we've seen before, if you want to estimate an expectation under some probability distribution, you're basically drawing samples from this probability distribution, you're taking the average, and you get the expectation. That's basically what Monte Carlo does. Dynamic programming, what it does is the expected values are provided by the model, right? So you can compute these expectations. That's what dynamic programming does. And you have to know what the transition function is to some of all possible transition states. But then you're using the current estimate v st plus 1 instead of the true value, right? Because we don't know what the true value is. So we go all the way down to here. We compute this expectation, except for we don't know what this term is. So we just replace it with our own estimate, v, current estimate. Okay, that's what dynamic programming does. And temporal difference is basically combines both. You sample the expected values, and then you use the current estimate instead of the true value function, right? So you're both drawing samples to estimate this expectation, and then you're replacing this term here, the truth, with your own current approximation. Okay? So at the end of the day, different methods, and then there are sort of extensions. You look at, we're not going to cover them in the class, but you should look at the book. It's your reading material. When there are something that's called TD1 or TD2 or TDN, which is essentially recursively updates what this thing is down, and then you kind of getting a little bit better estimators by rolling. It's almost like doing Monte Carlo in between. Instead of doing just one step, you can do multiple steps, right? And do this recursion here. So dynamic programming, if you think about, this is just a pictorial visualization of what, in a discrete state spaces, what the computational graph would look like if you could compute everything, right? You're in particular state S, you take an action, let's say there are two actions. Depending on the reward, you can get to state S prime, or maybe you can get to another state if it's a stochastic environment. You take another action, you can get to another state, and so forth, right? So if you think of this entire computational tree going all the way down, then dynamic programming just does the estimation at the top. So it computes the expectation over the actions, it computes the expectation over S prime and R, and then it replaces the true value function with your current estimate, right? So you're kind of like doing one step, almost like one step back up, right? It's exactly what you're doing. Monte Carlo approximation does the following. It basically says simulate the path in this computational tree all the way up to the terminal state. And the simulation happens according to your policy pi, right? So if some probability of taking an action, you flip a coin and take that action, right? And so you go all the way down to the terminal state. You get some reward along this path, whatever that discounted reward is, cumulative reward is. You're updating your value of the state towards that reward. Okay? That's a Monte Carlo approximation. Obviously, Monte Carlo approximation is unbiased because if you repeat this procedure many, many times, your mean will converge to the true mean. Your empirical mean will converge to the true mean, and you get the true value of the state according to your policy pi. Okay? And temporal different methods, it kind of combines both, right? So it's basically saying, forget about going all the way down to the terminal state, because that might be expensive, right? Maybe what I should do is I just do one step look ahead and just update my equation where, again, the target, RT plus 1 plus gamma times the value of approximation, your own approximation for what the value of the state should be. And you make an update that way. So you can see it's cheap. And this is very heavily used method. So if you've heard about Q-learning, if you've heard about deep Q networks, everything is kind of based on pretty much on TD learning. A lot of different methods, right? Sometimes people use Monte Carlo, and we'll talk about Monte Carlo tree search, where you're sort of trying to branch out a little bit further down. But instead of going all the way to the terminal state, you stop somewhere in between because it might be expensive. Like imagine you're playing a game, like in a game of Go. Simulating the board game all the way up to the end might be expensive, right? Sometimes you might want to do that, but in many cases, if you kind of end up in a where the value of the state is so bad, you know you're going to lose the game. There's no reason for you to go all the way down, right? So, and again, how much computation is a computational trade-off, right? The more you compute, the better your estimates are. So there are methods, as I mentioned, as TDN, where you're doing it through the n steps. So you can go all the way up to here, for example, and then you estimating the value function that way. Any questions? Yes?
You run the number of episodes and then know the value function, estimate value function from it. But in TD0, are you also running multiple episodes?
You can. So think about Monte Carlo. In a Monte Carlo, you're running one episode up until the terminal state, and then you can update the value of the state. You don't have to run 1,000 episodes. So it's a difference between batch learning and kind of online learning, right? How much of it, how much learning is happening, it depends on this alpha parameter, right? In practice, you run it once, you get the reward, you update your value function. You run it again, you get the reward, you update your value function.
Your value function is initialized randomly?
Yep, initialized, yeah. The value function can be initialized randomly. Just turn off my phone. Right. Yes.
For Monte Carlo, you only use it for episodic tests because you use it for terminal state. Can you use TD for continuous tests?
Yeah, that's speculative. We'll come back to that point. We'll come back to that. Right now, we're making an assumption that we're always working in the episodic tasks. In principle, I think you can, as long as this value is well defined. Right. So, in other words, yeah, I think you can. But we'll come back to this task. We're going to look at online learning and on-policy learning and off-policy learning with TD learning. So bootstrapping. Update involves an estimate, right? So what is bootstrapping? It's, yeah, question? Oh, so think of it the following. You always initialize the value of the state, let's say you initialize them random. Well, they're always 0 initially. So after the first update, for example, you can say, let's say all value of the states is 0. Your particular state, you take an action, you get big reward, right? And now you're basically saying, oh, something is wrong because now I have 100 plus the value of the state at the next time step is 0, right? But my current value of the state is 0 as well. So now I have a big learning signal. So now I raise up the value of my current state, right? And so forth. So next time, if I transition to that state from some other state, its value of the state is going to be pretty high because it's going to say there's a pretty good chance that if I take a good action, I will get big positive reward, right? So initially, everything is initialized randomly, and you're just applying that rule. You randomly sample the state, you do one step look ahead, you update. Randomly sample another state, one step look ahead and update. Again, we'll come back to the learning of this. I'll show you some code of how we can actually use temporal difference for doing the updates. So bootstrapping, it basically involves an estimate, right? Monte Carlo doesn't bootstrap. Monte Carlo basically says, run up till some terminal state and then look at what the actual reward I'm getting. So you're not really doing bootstrapping. You're not really using any estimates. Dynamic programming and temporal different TD learning, they do bootstrapping, right? So you kind of, your target involves your own estimate, okay? Sampling, the update doesn't involve an expected value. So Monte Carlo samples. You don't need to compute expectations, right? In particular, if your action space is very large or your number of states that you're in is very large, then Monte Carlo just samples. Dynamic programming doesn't sample. Dynamic programming actually computes the expectations. Obviously, if you can do that, that's probably more efficient. Every time you can compute expectations, your variance will shrink, right? As opposed to sampling. Every time you sample, your variance increases. But in many cases, you might not be able to use dynamic programming because you have to know how to sum over all possible transitions. So you have to have a model of what the world is like. Temporal difference samples. It's like a very cheap version of Monte Carlo where you're using your own estimate at the next time step as your own target. Yes?
So for methods that bootstrap, do your states near the leaves converge faster than the ones at the top of the tree or something?
Near the leaves. So typically you have better convergence for the states that are close to where the reward is.
Yeah, like the terminal states.
Yes. Obviously, it depends how you design the reward structure, right? Because if you're working in episodic tasks where rewards are only defined at the terminal states, then yes, this value function, you will be basically learning a lot around the terminal states. And this information will gradually backpropagate for the rest of the states. In some examples, you can get the rewards as you're executing actions, like partial rewards, right? In which case, you kind of do the learning of the entire environment. So that's why when you're designing reinforcement learning algorithms, there is something that's called reward shaping, which is to say, how do you design a problem so that you can provide your agents with rewards along the way? And that's kind of, comes down to, it's almost like if you provide the reward at every single time step, then it becomes very close to, not quite, but very close to supervised learning, right? Because if I take this action, I get positive reward. If I take this action, I get negative reward. Now I can just do supervised learning. I can say in this state, just take this action versus this other action, right? So if your rewards are very frequent, then learning becomes more stable. But if your rewards are rare or typically delayed, then learning becomes, much harder. And that's the beauty of reinforcement learning because you kind of sit in between, right? If you think about supervised learning, for every single input you have a target. If you think about unsupervised learning, I just give you data, you have no targets. You're trying to figure out what's going on in the data. And the reinforcement learning, I kind of give you signal, positive or negative, once in a while, right? And you have to figure out what your behavior should be to maximize, maximize positive signals. So policy evaluation. For a given policy pi, we want to compute the state value function v. And again, this is just as a reminder, I just wanted to remind you, again, this is what the Monte Carlo does. And the simplest temporal difference method, this is what it would do, right? Where this is the target. This is an estimate of the return. Now, you can also see that TD learning in general can be unstable, right? Because if your own estimate is wrong, then you're moving towards the wrong target, right? You can also see that the TD update is not unbiased, unlike a Monte Carlo. Monte Carlo is an unbiased estimate, but Monte Carlo is expensive. TD learning is cheap. Let's look at the example. This is an example that you have in the book, which kind of highlights the difference between Monte Carlo and temporal difference learning. So let's say that we are in, I guess in this case, 6 different states. I'm not sure what secondary road, secondary road, right. Okay, so you are in a state, elapsed time, how much minutes have passed, predicted time to go, and predicted total time. So, for example, predicted total time basically means how long is it going to take you to get home, right? And so let's say you're leaving the office, your predicted total time is 30. So you think you're going to get home in half an hour. You reach the car, you observe that it's raining. If you observe that it's raining, you're basically going to say the predicted total time is going to be 40 minutes. Right? Because that's how long I estimate it's going to take me. Right? Your current value function would say, I think it's going to take me 40 minutes. That's your own estimate. Then you exit the highway and you basically say, it wasn't so bad. So it's going to take me 35 minutes total time, right? Because I'm saving some time on the highway. And you take the secondary road behind the truck, you say, it's going to slow me down. So now I think it's going to take, total time is going to take 40 minutes, right? entering home, and so forth. So it actually took you 43 minutes. Okay? Yes?
Just to go back to the previous slide, I had a question about TD learning. What if the model of the environment is unknown? Do you need a complementary method to kind of get a good estimate of what the...
So we'll come back to this. We'll come back to this. We'll come back to the problem when we don't know what the model of the environment is. Okay? Right now, all we need to do is we sample the action according to the policy, and then also the environment should give us a state, the next state. So if we have a model, we know what the transition function is, we can use dynamic programming. If we don't know what the model is, we just observe what the next state is. And that's all we need for the temporal difference learning. Okay? So let's look at, so this is the setting, these are the states. So this is what the Monte Carlo would do. Monte Carlo would basically say predicted total time. The predicted total time is 43 minutes, right? So for every single state I'm in, right, I actually want to always predict 43, right? Because that's how long it actually took me to go from my office to my home. So you're running in this thing forward, you see it took me 43 minutes, right? And so at any point in time, your guesstimate, so initially you basically say, you know what, it's going to take me 30 minutes. And then you go to your car, you see it's raining, you're saying, no, it's going to take me 40 minutes. Well, as in actuality, it should take you 43 minutes, right? The temporal difference learning is basically one step look ahead. It's basically saying, well, if I'm leaving my office, my prediction is 30 minutes. But after I go to the next state, after I reach my car, my total prediction should be 40, right? And so now your target here, instead of 30, you're trying to predict 40, right? Because one step ahead, you're realizing it should be 40, according to your own estimate. Right? And so you go all the way up until you actually reach the actual outcome, right? Everybody sees that? That's a difference between the two methods. So TD methods do not require a model of the environment. You don't need to know what the transition distribution is over the states. You only require experience. You only require a sample from the model, right? So imagine a robot. If a robot takes an action, goes to the next state, if you actually had the model of the environment, you could actually say, what's the possible distribution of all possible states? Right, that I could possibly integrate over. In reality, you don't have that because you don't have the entire model of the world, but you observe what the next state is. And as long as you just have an experience, that's sufficient. So temporal different methods can also be fully incremental. So what that means is that you can learn before knowing the final outcome. Right? It requires less memory, it requires less computation. Now, when you say before knowing the final outcome, you also have to be a little bit, there's no free lunch, meaning that if you never observe the outcome, you can't learn anything, right? So you kind of have to be aware that, yes, you can learn without the outcome, but at the same time, most of the learning initially will happen around the terminal states, where the rewards are, right? And eventually get propagated to the entire environment. And so you can learn without the final outcome from incomplete sequences, okay, using your own estimates. And obviously both Monte Carlo and TD, they converge. And we'll talk about specific, in fact, if you look at the book, there are certain details of when they converge. Which one is faster? Which one do you think is faster? No? I think if you kind of thought that Monte Carlo was much faster, why would we even be talking about TD, right? So probably in many cases, as we'll see, that TD actually, performs much better in practice, particularly when you look at longer episodic tasks. We'll see some of that. Now, bias variance trade-off. So for the Monte Carlo, the update value, right? This is what the return is. The return G is an unbiased estimate for the value of the function, right? Because you're actually doing Monte Carlo sampling and you're sampling from the correct policy, right? So you get an unbiased estimate. In expectation, you get the right thing. On average, you always get the right thing. For the TD learning, you're updating the value towards the estimated returns, right? Now, here's the trick. The true TD target, if you knew the true value of the state at the next time step, this would be an unbiased estimate, right? And that's kind of trivial, right? Because if you know the truth and you're just doing one step Monte Carlo, then you get an unbiased estimate. But the target value, where you're replacing the true value of the state with your own estimate, which could be wrong, in many cases it will be wrong, especially initially when you're initializing the systems just randomly, then it's a biased estimate of V. Okay? But it's a biased estimate, which basically means on average you might not be doing the right thing, but it will converge. That's good. And also TD target has much lower variance compared to the actual return. The reason why is because if you look at your return G sub T, it depends on many random actions, transitions, and rewards throughout the episodic task, right? Temporal difference target, it only depends on one random action, transition, and reward. That's all. So in terms of the variance, you have a much smaller variance, which is good for learning, right? So you sort of have this, if you know about bias variance trade-off, there is always the trade-off, you know, how much bias you have in your algorithm versus how much variance, right? And so two of them are trading off each other, and that's the same things happening here. So Monte Carlo has high variance because it depends on a lot of random actions that you're taking, but has zero bias. It has good convergence properties, even with function approximation. So sometimes later on we're going to look at class and we're going to use neural networks as our function approximations for the policies. It's not very sensitive to the initial value, very simple to understand and use, right? You just execute your policy, look at what you get, and sort of recover. In fact, Monte Carlo is used a lot in financial industries, right? You sort of set up and you're running these simulations of how the markets would behave, you know, for the next year. And then you try to just figure out like what would happen if market behaved this way and this way and this way and so forth, and you just average. So Monte Carlo is heavily used basically in a lot of different areas. But TD has low variance, some bias, obviously. It's good, usually more efficient than Monte Carlo. TD0 will converge to the value of the state under certain conditions, but it's more sensitive to the initial values, right? If your initial values are crazy, it's going to take a while to converge, right? If your initial value would say, this is a really amazing state, it's like a pride, it will take a long time to override it, right? Because you're going to be updating, saying, no, that's not a good state. So let's look at the example. This is a random walk example. So what happens here, you start at state C. With probability half, you move to D or B. And every time you move, you get 0 reward. And you only get the reward of 1 once you reach the terminal state. And you get the reward 0 if you reach the other terminal state. Okay? So this is what the estimated values would look like. So this is values learned by TD after various number of episodes. This is the update, and you can see that this is the true value. It's just a diagonal, right? Because being in this state is really bad. Being in this state is worse. Being in this state is even, you know, probably around 0. That's what you have here. Being in this state is better. Being in this state is fantastic, right? So that's why you have this curve. And so you can see after 10 iterations, you get some approximation. After 100 iterations, you're basically recovering the true value function for this particular example, where the policy is just moving half and half in each direction. So, and this is what the root mean squared error averaged over the states look like. This is data averaged over 100 sequential sequences of episodes. So here what you're seeing is the Monte Carlo is kind of doing the worst. TD learning can do better, but it's also quite sensitive to the learning rate, right? So for different learning rates, you have different convergence. So it's kind of like, you know, if I go back just for a second here, what is this thing? You get sensitivity to this alpha, right? The reason why you get a little bit of sensitivity to the alpha is that, you know, if some of you looked at neural nets and how people are training neural networks, learning rates are pretty hard thing to tune, right? And for neural nets, for supervised learning, you actually know what the target is. Here, you have to set up the learning rate where you have a noisy target, right? The only true signal you have in this update equation is the reward. Like, was it a good or was it a bad? If your reward is 0, then this is your estimate, noisy estimate of what this thing should be, right? So your learning rate now becomes much more sensitive when you are using these methods for doing learning. So it's a fairly sensitive hyperparameter to use. You can also do batch learning or batch updating. So you can train completely on a finite amount of data. Instead of running one episode and updating it, you kind of like do it in batches. Same thing as you would do for regular training. So for example, you can train repeatedly on 10 episodes until convergence. And then you can compute updates according to TD or Monte Carlo, but only update estimates after each complete pass through the data. So you can do batch learning much like you're doing batch learning in sort of traditional supervised learning algorithms. Okay? And you can basically show that on the finite Markov prediction task, and again, we're working with finite state spaces, finite actions. On the batch updating, TD converges for sufficiently small alpha. So you can sort of like show there's certain rates on the alpha that you can push, and you can guarantee convergence of TD learning to the correct value function. Okay? If you're interested in theory behind convergence of these algorithms, have a look at the book. There are a few kind of highlights on what the conditions are on the learning rate. It's sort of similar to Robbins-Monroe, like your standard, 1 over alpha, I think, is it 1 over alpha, the sum of 1 over alpha should diverge, but what sum of the 1 over alpha squared should converge, something like that. So constant alpha also converges under these conditions, but may converge to a different answer. This is an example of, again, random walk behavior and the batch learning, Markov chain, Monte Carlo versus TD learning. And again, you can see that as you add new episodes, so 25 episodes, 50 episodes, 75, 100 episodes, one in this case is converging a little bit better than the other one. Okay? Let's look at another example to highlight the difference between maximum likelihood estimation and TD estimation, or Monte Carlo and TD. So imagine that you observe the following 8 episodes. That's what you see in your data. Okay? Suppose that you are in state A, you take an action to go to state A, you get 0 reward. You transition to state B, you get 0 reward. Okay? Then you start at state B, you get 1, and at some point you start at state B, you get 0. Okay? So what about a new assuming Markov states, no discounting? So what about the following? How many of you think that the value of the state A is 0? Doesn't it look reasonable according from this data? You only get to observe state A once, and then you basically get 0 reward. You go to state B, you get 0 reward, and so you only see A once in the sequence to get 0 reward. Maybe the value of the state should be 0. Right? So let's look at this. Let's look at this particular Markov model. So you start at state A. With probability 1, you transition to B, right? You transition to B, but your reward is 0. With probability 0.125, with probability 1/4, you go to the terminal state and you get the reward 0. With probability 3/4, you go to another state and you get 1. That's exactly what's being described here, right? So this is a Markov model for this example, right? This is the Markovian setting. So now, what's the value of state A? Clearly, the value of state A is 0.75, right? Because what happens if you're doing Monte Carlo, you start at state A, you go to B, and then with probability 0.75, you get 1. So your overall discounted reward is 0.75. With probability 0.25, you go to another state. So that's why it's 0.75. So, but if you look at this particular example, the prediction that best matches the training data is the value of state A should be 0, right? And this minimizes the mean squared error on the training set. And this is what a batch Monte Carlo method gets. So if you just push everything together, this is what's going to happen. This is maximum likelihood estimation, because if you look at this example, you start at A, you get 0. That's it. And you never observe any other transitions from A. But if sequentially as the problem, then we would set VA to be, the value of the state to be 0.75. And this is the correct maximum likelihood estimate of a Markov model generating the data, right? So if we do a best fit Markov model and assume it's exactly correct, then we compute what it predicts, right? And this is sometimes called the certainty equivalence estimate, and this is what TD, temporal difference method, would get for you. Okay, so summary so far. So we've looked at the one-step tabular model for TD learning, right? And as we'll see for the rest of the course, TD learning will form the basis for a lot of different algorithms. We're going to look at some of them now. These methods bootstrap and sample, right? They bootstrap because you're using your own estimate, but they also sample. You're combining aspects of dynamic programming and Monte Carlo. So they kind of like combine the best of both worlds. TD methods are computationally kind of nice, right? That's why people are using them. And if the world is truly Markov, then TD methods will learn faster than Monte Carlo methods, if you actually have the truly Markovian setting. Now, if it's not, then it's not clear. So if you look at kind of this view of different methods, you have temporal difference learning here. If the width of the backups, if it's small width of the backup, you get dynamic programming, right? If you hide the depth of the backup, you get the Monte Carlo methods, right? So the Monte Carlo methods is really going all the way to the terminal state. Dynamic programming just looks at one step look ahead, but computes the expectations exactly. And this would be your exhaustive search. If you could do exhaustive search, then you could just solve the problem, obviously, right? So let's look at how do we do learning and action value function, the Q function. And we'll see that the Q function is actually an instance of TD learning. It's a temporal difference learning. And Q learning, sometimes called Q learning, it's like one of the oldest algorithms, and it's pretty much, in many cases, is sort of the state-of-the-art algorithm. So let's say we're trying to estimate the Q function for the current policy. Okay, so we're given the policy, we're in the state, we take an action, generate the next state, we take the reward. Obviously, the reward could be 0. We get to the next state, we take an action, we get the next reward, and so forth. Right? So we have this sequence of taking actions, transitioning, getting rewards, and such. So at every transition from a non-terminal state S, we do the following update. The Q function from state S, taking action A, is going to be updated by this expression, right? where we look at the next time step, we look at the reward, we look at the discounted value of our own estimate of what Q function should be, minus what the original Q value is, right? This is called Q learning, and if ST is the terminal state, then you basically set Q to be 0, because you've stopped. There's nothing more to go beyond that, right? So if you hit the terminal state, if you get some reward, maybe big positive or big negative, the next Q function is 0, and then you're just trying to match the two. Okay? Any questions? Yes.
So what is 8 equals 1 in this case?
Sorry, what is what?
Argmax over 8 equals 1 for...
What do you say, Argmax?
Should there be one? So it's governed
No. So for now, no. This is just a standard learning reaction. We try to evaluate the function Q. Later on, we'll get to the Argmax. But for now, you just execute a sequence, and you're just matching them.
So you are at ST, you took an action 80, you reach ST plus 1.
Yep.
What's 80 plus 1?
Oh, you take another action according to your policy. Right? You're simulating your episode forward. So you're always taking action according to your policy pi. So pi is always given to us. Right? All we're doing right now is just evaluating the values of the states of the action value function Q. Once we have a Q function, then we can update our policy. Okay? So this is something that's called own policy TD learning, right? There was a question, can we do own policy, sort of like online learning? And yes, we can. This is what's actually happening if you're executing action, you take an action according to your policy, you get to the next state, you get the reward. Again, you're executing action according to your own policy and so forth. So this is on policy learning, right? And you're evaluating Q function. So you initialize Q values arbitrary, and Q terminal state should be 0, and you repeat for each episode. So for each episode, you initialize some state, you choose action from state S using the policy you can derive from Q. Okay. Now, initially, if you think about, I think what this is doing, this is actually on policy DD control. This was trying to figure out what the Q function is, but now we're actually trying to learn what the policy should be. Okay, and it's fairly simple. You basically you're taking action A from state S using policy derived from Q. Right. So initially your Q just initialized to some random values, maybe they're all zeros. And perhaps your Q function could be an epsilon greedy function, which is you choose the action with a maximum Q value with some probability, and at 1 minus epsilon, you're choosing some random action. And then you repeat for each step of the episode. You choose action A prime from state S using the policy again derived from Q, and then you update your Q function. And then you update your state and update the action. Make sense? So it's almost like what you're seeing here, what you're seeing here is you're seeing if I actually execute the whole thing using policy pi, I could compute the Q value. What you're seeing here is you're basically saying, you know what, my policy can be derived from Q function, which is pretty easy. You just take the maximum value of the Q function when you're taking a particular action. That's the optimal policy according to your Q estimates, right? So just use that policy, and then you update your Q function. And then again, you can update, take another action, update the Q function. Take another action, update Q function. So that's why it's called own policy TD control, because you're executing policy and you're improving it as you're executing it. Right? Up until you reach some terminal state. Yes?
Does this algorithm try to explore all the state and action?
This is going to be controlled by epsilon. Right? So you need the epsilon here so that you explore enough sufficient number of actions and states.
There's no policy improvement here.
There is a policy improvement here. You're updating your policy according to, think of it this way. The relationship between Q and policy, if I have a Q function, what's my optimal policy? Argmax. That's all. Right? So when I say take an action from state S using policy derived from Q, that's where you take argmax. If you basically say, I just want to evaluate my policy, I don't want to improve my policy, I just want to compute what the Q function is for my policy pi, then you would sample actions from policy pi and update the Q function. That's exactly what's happening here. Right? So this is evaluation, and this is on policy control, meaning that you are updating your Q function, which means that next time you're taking actions according to Q function derived from the update. Yes?
So is it better to choose which state I will update is based on my sample, or I can choose randomly?
Right. So this one is SARSA, and then sorry, I should have mentioned that SARSA stands for state action reward state action. Right. So which is literally what you need to update the Q function. You need five things. The question is, should you choose the state, a particular state? This is particularly the algorithm that's called on policy, which basically means, imagine you're running a robot, right? So you can't really take, well, place this robot over here, see what happens. Or like place the robot over there, see what happens. The robot just executes things forward. And as the robot executes things forward, the only thing you can control is you can control how much exploration you want to do. That's why it's called on policy, right? There are something that's called off policy learning, which is basically, think of it in virtual environments. Let's say you can place robots, and then you can choose what state to start from, right? So here's an example of a setting where you are in a state where you have an undiscounted episodic reward is -1 until goal. So your reward is always -1 up until you hit the goal. So you basically, what you want to do is you want to find the minimum path from state to the goal state. Except for here you have a force that basically shifts you up. So if you go, for example, and this is how much the force is being applied. So if you go to this cell here, the force by 2 will basically push you up by 2 cells, right? So in other words, if you try, and then this will push you up by 1 cell. So every time you try to go this way, you actually get pushed up by the wind, right? And so this is an example of using SARSA on policy algorithm. So you're kind of like simulating it forward. You're just updating it as you're simulating it. And this is the optimal path. It's a little bit weird characterization of the curve, but what this curve is essentially supposed to say is that as the number of tiny steps increases, you basically can pretty much find the optimal path. Okay? So you always kind of move around in the environment. And this is kind of, it's interesting, this is the optimal path. Because there's no way for you to, maybe you could actually like go this way and like get pushed a little bit up to here. That might be another optimal path, but this seems like this is one of the optimal paths you can find. I actually don't know whether you could do something like this and sort of like get pushed up, and then get pushed up by, might be difficult to do. Okay, now we've talked about on policy. Now let's actually look at the Q learning, which is off policy, right? And this is one-step Q learning. So off policy basically means that, you know, we're not running continuous policy. We can choose the state action. We actually don't need to have access to the policy. The beauty of Q learning is that you don't actually need to have a policy to learn the Q function, which is kind of, if you think about it, it's kind of weird, but it's interesting. So this is one-step Q learning. So one-step Q learning basically says update my Q function. If I, in particular state, I take action, AT, I get the reward, I get the next state, and then what I get to do is I choose the maximum over all actions of my estimated Q function, right? Minus my current Q function. Okay? So what does this mean? Yes?
This is implicitly assuming that in the next step, your policy is to choose the best action.
Yes.
So there is like an underlying policy.
Well, but it's your own kind of policy queue. you're trying to learn your own policy, right? So Q is your own estimate of what your own policy should be. And you're taking an action at the next time step according to your own optimal policy, not someone else's, right? So maybe we can look at the algorithm and then just basically look at what we actually need to learn this algorithm in just a second. So we're initializing Q function and then initialize the state. So notice that initializing the state, we can choose states randomly from our environment. We choose action from state S using policy derived from Q. So for example, using our own Q function, right? And then take an action A, observe the reward, the next state, and then update our own Q function this way. Right? And then do the S. Yes?
Yeah. If it is an all-policy control, is there any need to use the policy derived from Q, like epsilon greedy policy?
You mean like, is there something other than epsilon greedy?
Can we just use any other policy, but do we really use
Yeah, so good question. Can we use other policy to choose action A, for example? The only thing that we're doing here right now is what is it that we need to do to update Q-learning? We need the initial state, we need the action, and that's all, right? Because the environment gives us the next state, and then we're basically choosing the next action according to our own policy, right? So the only thing that we need for this algorithm is state and action. In principle, in practice, if you set your epsilon to be high enough, then your policy is random. So you basically say, pick the state, pick the random action, see how good is it. Update the Q function. Pick another random state, pick another action, see how good the update is, right? So update. So in many cases, what happens in practice in Q-learning is that you basically, at least initially during learning, you're basically creating a whole list of, if I'm in that state and I take the action, what the next reward and state would be. If I take this state, I take this action, what the next reward and state would be, right? And you can kind of relearn, you can learn on this. It's like your training data. Think of it as almost like a supervised learning. You create this list once, it's called replay memory, and then you're just updating your Q function, right? Which is kind of interesting because you don't need the policy to kind of, do it. You just can pick states and actions, and sort of as long as you're covering states and actions, there's some non-zero probability of choosing a state and choosing the action, you will find sort of the optimal Q function. Yes? Oh, go ahead.
Could you compare a little bit about what you mean by off-policy and on-policy?
Yeah, so own policy, if we come back to the own policy learning, so own policy it really is kind of in this setting, right? The own policy is that you're executing policy as it goes along. Off policy is you only need state, action, reward, state. And the next state has nothing to do with the previous state. Own policy is that you take a state, action, reward, the next state. And then from the next state, you take an action, you get the reward, you get the next state. And from the next state, you get the action, reward, and the next state. So think of it as like chain sequence. It's the whole thing that you're generating. Off policy learning is really, you don't really have any policy here. Sorry, you don't have any policy here. Just take state action, how do I update Q? State action, how do I update Q?
So this is like a TT0 with a policy improvement.
Yeah. That's right. Question? So this forms the instance of Q learning, right? In fact, you can construct the training data for it, right? You can just pre-construct the training data for it. You can just go select action state, compute what the reward, what the next state is. That's it. You need 4 things, right?
Question?
Yeah.
So what's the difference between Q-learning and SASA?
So SARSA in this case is you kind of like, well, in this case you're kind of getting, here you're kind of getting the next state. So you have to have state, action, reward, state, and you have to get another action, right? And another action you're going to be getting either from some epsilon greedy or from some other policy, right? right? If you look at off policy, you're always picking the maximum. So you don't need another action. So SARSA requires you to have an additional action that you're learning from according to your own policy. This one doesn't. So the two things are very close to each other, but SARSA is typically applied in online setting. Q-learning is applied in off policy. But again, they're fairly close to each other because you can always say, if I choose the next action according to the epsilon greedy or some other policy, then I just replace this with whatever that action is. So this is just one example. And again, this is Q-learning versus SARSA. Whereas in Q-learning, you always pick the maximum action according to your own policy. In SARSA, you're sampling what the next action should be. And this is an example of reward per episode. So you can see that in many cases, this is the optimal path. And this is the safe path, right? So in many cases, if you're choosing this path, you don't want to do epsilon greedy, right? You don't want to choose your states according to the epsilon. You really want to just pick the max. Because if there's some probability that you're going to jump off the cliff, you get big negative reward, right? So in these cases, well, it's not clear whether Q-learning would do better because with Q-learning, it's kind of hard to learn as well. SARSA, I think in this case, SARSA will choose a little bit more of a safer path because you're giving it a little bit of randomness, so it's not going to choose that particular path. There is another class of algorithm, but again, as I mentioned before, the two algorithms are very similar to each other. A lot of it depends on what the next action is, right? In Q-learning, you only need state and action. And then you just do learning, and then your next action at the next time step is the maximum according to your Q function, right? In SARSA, you choose the next action according to the policy, epsilon greedy or something else. Or typically, it would be epsilon greedy because you want to learn what the Q function is. Now, yeah.
So is Q-learning guaranteed conversion?
Yeah. So we'll come to the convergence in some of the future classes. A lot of it depends on what the state space is and how you sort of running it. In a tabular environments, yes, Q-learning will converge, and the certain assumptions will converge to the optimal. The other thing that you can do is you can use expected SARSA. So think of expected SARSA is when you're updating your Q function, but notice what happens here. Instead of picking the maximum action, or the action with the maximum Q function, you're actually taking expectation over all actions according to your policy, pi, your current policy. Right? So if you're using expected SARSA, so if you can compute this expectation, then expected SARSA typically performs better than SARSA, but it costs more because you have to compute this expectation. Think of it as follows, where instead of choosing the next action using Q function, which is the maximum value of the Q function, you actually can derive what the policy is and take an expectation of the Q function, right? This is typically the example where, let's say, you're in a particular state. If you take this action, your Q value might be 10. If you take this action, your Q value might be 9.9, right? Now, with a Q-learning, you choose this action, and you basically just proceed with that. With expected SARSA, you would average over both of these actions, right? And that typically, every time you can integrate out or average over possibilities, obviously that reduces the variance. And if you have a variance reduction, then you have better convergence. Obviously, it will cost you more. Yes?
So if I want to use expected SARSA for control, how can I update pi?
Yes, a good question. How do you go from Q to pi? That's sort of a very good question. I think in many cases, what people typically end up doing is you're basically saying, if I have Q values, I can use Boltzmann distribution, which is kind of pushing it through the softmax. Think of it as E to the power of Q divided by sum of all possible actions. So you're kind of like saying if two actions have similar Q values, they should have equal probability of being chosen. And how exactly you do the conversion is a little bit tricky, but there are ways of doing it. Think of an expectation here as a way of basically saying what I want to make sure is that if I'm in a situation I have 2 or 3 actions, all of them have similar Q values. If I could integrate over those, I would have a reduction in my, as opposed to doing like a greedy approach, we're always picking the best one, right? And that's also, instead of always picking the best one like you're doing here, SARSA is actually picking it according to epsilon greedy, according to the Q, right? So there's some probability that you might choose a completely different action. And this is just a kind of, if you look at performance, one thing that, there's expected SARSA that works pretty well. There's asymptotic performance, there's a Q learning, there's Q learning with different alphas. And so generally, and depending on what your learning parameter is, you can see the performance can be drastically different, right? So for a fixed alpha, there is no guarantee that you will converge to the global optimum when you're doing Q learning, right? So the conditions on the learning rates, much like stochastic gradient descent or gradient descent. If you fix a gradient descent learning rate, there's no guarantee that you will converge to the local optimum. You just like go to the local one, you just keep bouncing around until you decrease the learning rate. And how you decrease the learning rate and conditions on it, you can kind of study that. But under certain conditions on the alpha, on the learning rate, you can show that it will converge to some, will converge to the optimum. Any questions? I think in this case, it was in the book. I think that in this case, it basically means the best possible performance of SARSA. I think in this case, asymptotic performance, and I think in this case, it's an environment that was fairly small. If you go here, you can basically enumerate and do brute force and compute everything, right? And compute the global optimum. So in this case, it's a little bit funny that expected SARSA is actually doing so well. Yeah. But this plot, I just wanted to include this plot to highlight that if you look at Q learning, if you look at SARSA, they kind of very close to each other, but could be somewhat different. The most important thing I wanted to communicate is the learning rate. And you can see that the behavior of these algorithms can be very unstable, right? So there was a recent paper coming out of Joël Pineau at McGill that basically showed that with different random sits and different initializations, the performance of the algorithms can be very big, right? In fact, they were able to show that if you draw it like random seeds 5 times, and you look at kind of the bandwidth of the algorithms, you draw random 5 times again, and the algorithms can behave very drastically different, right? Which comes from the fact that sometimes it's difficult to say, oh, is Q learning working better than SARSA? Or is it just so happens that SARSA had a really bad initialization, right? So I can tilt my hyperparameters and I can make any one of these algorithms work better than any other one, right? With the appropriate choice of hyperparameters and random seeds, which basically tells you that you should be very careful when you start doing homework. I think homework, the second homework, you're going to be training deep Q networks, which is an extension of these models, Q learning, to combining them with deep networks. And you will see that you have to be very careful how you are training these models. So summary, let me just summarize. We've looked at the tabular model-free TD learning methods. These methods bootstrap and sample. And again, when we actually start looking at the deep Q networks, you will kind of see that this problem exacerbates. This problem becomes worse, the bootstrapping problem, right? It's a very bizarre kind of setting where you're using your own estimate as your own target, which introduces a lot of instability. But there is no other way for you to go around it, right? Because the only true signal you have in all of these methods is the reward, right? Everything else is just you're kind of just trying to fit things around. The only true signal you get are the rewards. So if your rewards are sparse, no matter what method you use, it's going to be very unstable. But at the same time, it's remarkable what people were able to do in the last 3 or 4 years with these methods. I think a lot of it comes from the compute power, because you're basically saying, I couldn't do it on CPU 10 years ago, but I can just run billions of simulations. And now I can do it because that's fine. It's like trade-off between how long your rewards are versus how much compute you have, right? Because eventually you'll hit the right rewards and do the right exploration. Actually, the biggest problem right now, also, if you take these methods and apply them in real robotics, so for real robots, then it's not clear, because with real robots, you can't run billions of simulations, right? So TD methods are computationally very nice. If the word is Markov, then TD methods will learn faster. And so we've looked at on-policy control, right, where we just execute state, action, reward, state, action, reward. So it's a continuous policy, and we're improving this policy as we're going along. And again, this is called online on-policy learning, because you're executing the policy and you're learning what that policy is. Off-policy control, Q-learning, off-policy is that you don't actually have a policy. You just have state action and you're learning. And you have another state action and you're learning. So this is very nice, kind of like later on, again, when we look at more models like deep Q networks and others, typically people just create these massive histories of state action, what would happen, state action, what would happen, and you can do learning based on kind of this fixed, almost fixed training set, right? On policy, you don't have a fixed training set. In on policy, you're kind of executing the policy, you're adjusting your own policy, you're executing policy, and then you're adjusting your own policy. So you're always taking actions according to your own policy and adjusting it. For Q learning, you don't have to do that, right? You're just storing state action, next state reward, state action, next state reward, right? Is that clear? The difference between the two? Yeah. Okay. So good. So next class, your first assignment is going to go out on Monday. One thing I should note is that if you don't have Gradescope account, contact TAs. Okay? Because your assignments are going to show up on Gradescope and your submissions are going to be on Gradescope.